Hi everyone, welcome to My Chemistry Hub. Sherry Ann here, and today we'll be looking at CAPE Unit 1 past paper question. Just a simple question from Module 1, Fundamentals in Chemistry. So let's go. So this reads, the valence shell electron-pair repulsion theory, that's the VSEPR theory, is normally used to predict the shapes and bond angles of simple molecules and ions. State the basic principle behind the VSEPR theory. So I'm going to do just a mini presentation about the VSEPR theory. So as the question says, it's used to predict the shapes and bond angles of simple molecules and ions. But how does it do this? So this theory suggests that the electron pairs, that surrounds the central atom, the electron pairs that surrounds the central atom, one, they repel each other. Just trying to spell. So they repel each other, and not only that, in repelling each other, they arrange themselves in space to reduce the repulsive force. So they repel each other because like and like repel. And two, they arrange themselves in space. They arrange themselves in space to reduce this repulsive force. So I just talk about electron pair, repulsive force. Just spoke about electron pairs, but what are these electron pairs that I'm talking about? So the electron pairs consist of two. So you have bonding pairs. They actually take part in bonding. As the name suggests. And you have lone pairs. They do not take part in bonding. Lone pairs, right? All right, so for instance, the ammonium ion, NH4 plus. The ammonium ion. All right, let's draw it. Let's draw the ammonium ion. See if I can draw it so that you can see. Draw it so you can see. And then you have this here. This. And this here. Yeah, and then it's an ion. I got this. So you can see it has 4 electron pairs. 1, 2, 3, 4. And all of them are bonding pairs because they're taking part rather in bonding, right? So what happens is that the bond will arrange the bonds 1, 2, 3, 4 that I just highlighted. They will arrange themselves at maximum distance to minimize the repulsive force, right? Remember we're talking about the repulsive force, repulsive forces. So the bonds in the ammonium ion, they have 4 electron pairs. All our bonds, all our bonding pairs, they will arrange themselves in space to reduce the repulsive force, and then this will result in the molecule adopting a tetrahedral shape. Tetrahedral shape with a bond angle of 109.5 degrees. 0.5 degrees, right? So what about if also what I need to highlight in this is called the bonding pairs repelling each other. This is called bonding pair repulsion. So what if it has, so just spoke about ammonium, it has 4 electron pairs, all are bonding. What if it has 4 electron? What if the molecule rather has 4 electron pairs? But in this case, you have 3 bonding pair and one lone pair. What happens in that case? So let's look at a molecule that has 4 electron pairs, 3 bonding pair, 3 bonding pairs, 1 lone pair. Let's look at ammonia. So just look at ammonium. Let's look at ammonia. And let's draw it. All right, show you a better picture. You have your lone pairs there. So I can draw it. That's H and H. And then you have this. Oh, that's a bit too long, but you get the gist. So in this case, what will happen is that the electron pair will want to arrange themselves in tetrahedral shape, they'll want to do that. But due to the presence of the lone pair here, they will push the bonding pair closer together. So the lone pair pushes the bonding pair closer together. Or repels them. So they repel them closer together, right? So instead of adapting a tetrahedral shape that it wants to adapt, it adapts to a trigonal pyramidal shape. Pyramidal shape, right? And this has a bond angle less than 109.5 degrees, so approximately 107 degrees. So in this, you have lone pair bonding pair repulsion taking place. Lone pair bonding pair. So because of lone pair bonding pair repulsion, it adapts a trigonal pyramidal shape. Repulsion taking place, yes. So lone pair bonding pair repulsion. And remember this angle, right? 107 degrees, approximately 107 degrees bond angle, less than 109.5. All right, so let's look at the last one. Say it's still, it has 4 electron pairs, but in this case, it has 2 bonding pairs and 2 lone pairs. What kind of molecule have 2 bonding pairs and 2 lone pairs? What kind? Of course, water. You are correct. So water has 4 electron pairs, 2 bonding pairs, 2 of them takes part in bonding, 2 lone pairs. So let me go ahead and draw that for you. Gonna draw it accurate so you know what's happening. Water. So you know you have oxygen, you have 2 lone pairs, you have H. All right, just for simplicity here. H there. So what will happen in this case is that you have the lone pair of 2 lone pairs now repelling the bonding pair rather together, repelling them together, and you also have lone pair repulsion. So this will result, right? This will result in the molecule adapting. It wants to adapt the tetrahedral shape, but because of the presence of the lone pairs, it adapts a V shape with a bond angle less than 109.5 degrees, approximately 105 degrees, right? So you have lone pair bonding pair repulsion, and you also have lone pair repulsion. Lone pair, I have a bond over here. Approximately 105 degrees. You have lone pair repulsion. So the repulsion that we learned about, so in ammonium ion, then that you have bonding pair. Ammonia, we saw lone pair bonding pair repulsion, and in the water molecule, we're seeing lone pair repulsion. So lone pair repulsion, okay, I'm going to put this for short, is actually the strongest one. So you have lone pair repulsion, and then lone pair bonding pair repulsion, bonding pair repulsion, and then the bonding pair repulsion. All right, so the thing about these bond angles and shapes, and the electron pairs, and how much the number of bonding pair they have and the number of lone pairs they have, you kind of have to commit that to memory, right? So say for instance, it has 5 electron pairs, right? And it has all our bonding pairs. Yeah, that's that. All our bonding pairs. You have to commit to memory that. Look, in this case, you'll have the shape would be trigonal, bipyramidal, and the bond angle will be the bond angle in this case would be 120 degrees and 90 degrees. So for any case that they throw at you, whether it has 6 electron pairs, 5 electron pairs, 4, 3, 2, either have one lone pairs, all are bonding, or whatever the case may be, you just have to commit to memory how the electron pairs and the number of bonding pairs and the number of lone pairs, what the shape and the bond angle would be, right? All right, so let's go to the next part of the question. When hydrochloric acid reacts with water and ammonia, the corresponding hydroxonium and ammonium ions are formed. Using the VSEPR theory, state the shapes of the hydroxonium ion and ammonium ions using suitable, that's part 1. Part 2, using suitable diagrams to illustrate the shape of each ion. And part 3 says account for the shape of each of the species. We already looked at ammonium ion earlier. Let's look at the hydroxonium ion. Hydroxonium ion is just water with another hydrogen, right? So let's draw it for you. Hydroxonium. Yes. Let's draw it so you can get the there are lone pairs there. It's an ion, hydroxonium ion. So as we can see how much it has. It has 4 electron pairs, right? We see that. 4 electron pairs. And we can see that it has 3 bonding pairs, 1 lone pair. We just did something like that, right? We just did it, like ammonia, right? So it results in so it says use suitable diagram to illustrate the shape. Right? Account for the shape. The shape would be, yes, you are correct, trigonal pyramidal, and the bond angle less than 109.5 approximately 107 degrees. But why? It says account for the shape. Why is it that it has this shape? Trigonal pyramidal, I mean. Why does it have this shape? Of course, you're going to mention lone pair. Of course, you have to mention lone pair, bonding pair, repulsion. Bonding pair, repulsion. Yeah, right? Because it wants to adapt a tetrahedral shape. However, due to the lone pairs the bonding pairs, repelling the bonding pairs closer together, right? It does not take this tetrahedral shape, but instead adapts to a trigonal pyramidal shape. So that's how you account for the shape of the species. Okay, and that's the end of our session for today. I hope you learned something. Thank you. Remember to like, share, and subscribe. And I really hope that you learned about VSEPR theory, what could account for the shape of the molecule, and that includes the electron pairs, the number of bonding pairs it has, lone pairs it has, and how that, as I say, yes, accounts for the bond angle, and also the shape of the molecule. So join us again next time. Okay. From Sherry. Bye.